Hello everyone, I am Sajjad Hajian from Electrical and Computer Engineering Department, Western Michigan University. On behalf of my co-authors, I am presenting our work titled Chlorine-Terminated Titanium Carbide MXene as Nitrogen Oxide Gas Sensor, First Principles Study. This is the outline of my presentation. In the introduction, I will talk about the applications of gas sensors and will introduce 2D materials and MXenes. Then I will talk about gas sensing of titanium carbide MXene. In the computational methods, I will talk about the methods used for optimizations and equations used for calculations. Next, I will present and discuss the results followed by conclusion and future work. Gas sensors have been used for various applications including food quality control, air quality monitoring, hazardous gas leak detection, and medical diagnosis. Two-dimensional materials have thickness-dependent physical and chemical properties and high surface-to-volume ratio. 2D materials have been used for the development of highly sensitive and low-power sensors, which can operate at room temperature. The gas sensing mechanism is the charge transfer between 2D materials and adsorbed molecules. MXenes are a new family of 2D materials. MXenes are receiving a significant research interest in applications including biosensing, energy storage, hydrogen generation, and developing antennas. Recently, the gas sensing properties of MXenes have also been investigated. A room temperature ammonia gas sensor based on titanium carbide MXene has been developed, showing the promising performance of titanium carbide MXene as ammonia sensor. Also, a highly sensitive and low-noise MXene-based gas sensor with a very low limit of detection has been used for the detection of volatile organic compounds at room temperature. MXenes are typically formulated as Mn+1 and Tx, where N can be 1, 2, or 3, and M is an early transition metal, X is carbon or nitrogen or both, and Tx refers to surface terminations such as fluorine, oxygen, and hydroxyl groups. MXenes have a layered structure where each X layer is placed between two M layers as shown in the figure. Until very recently, the surface termination of synthesized MXenes were typically a mixture of functional groups. A new MXene with exclusive chlorine surface terminations has recently been synthesized and added to the family of MXenes. In MXene-based gas sensors, the mechanism of gas sensing is dependent on the charge transfer between the gas molecule and MXenes, which changes the conductivity of MXenes. So it can be very useful to investigate the gas sensing properties of chlorine-terminated MXene and compare it with MXenes with other surface functional groups. In this work, the first principles study was employed to investigate the gas sensing characteristics of the chlorine-terminated titanium carbide MXene. The first principles study was employed to investigate the gas sensing properties of chlorine-terminated titanium carbide MXene. The DFT calculations were used in this study. DFT is a computational quantum mechanical modeling method for many body systems. The software used for implementing DFT calculations was Siesta, which is a package for performing ab initio DFT calculations. To analyze interactions between gas molecules and the substrate, the adsorption energy and charge density difference were calculated. The equations for calculating adsorption energy and charge density difference are shown in the right bottom of the slide. Initially, the geometrical optimization of MXene supercell was performed. The chlorine-terminated titanium carbide MXene supercell is illustrated in the left top figure. As listed in the table on left bottom, the lattice constant of the chlorine-terminated titanium carbide MXene was obtained as 3.22 angstrom, and the distances between the titanium atom and carbon and chlorine atoms were obtained as 2.16 and 2.5 angstroms respectively. The most stable structure for the adsorption of the nitrogen oxide gas molecule on the chlorine-terminated titanium carbide MXene is illustrated in the figure on the right. As shown in the figure, the nitrogen oxide gas molecule was adsorbed above the titanium atom. Also, the nitrogen oxide molecule is adsorbed on the chlorine-terminated titanium carbide MXene almost vertically, with the nitrogen atom closer to the MXene. The atomic distance for the adsorption of the nitrogen oxide gas molecule on the chlorine-terminated titanium carbide MXene are listed in the table on the right bottom. In the most favorable system configuration, the distance between the nitrogen atom and the oxygen atom, the nearest chlorine atom and the nearest titanium atom are 1.16, 2.76, and 3.73 angstroms respectively. The adsorption energy for the most favorable system configuration was calculated as negative 0.5 electron volts. As shown in the figure on the top right, there is no chemical bonding between the nitrogen oxide gas molecule and the MXene, which supports the physisorption of the nitrogen oxide molecule on the chlorine-terminated titanium carbide MXene. Some other MXenes have been previously reported as promising materials for the detection of nitrogen oxide gas. The adsorption energy for the adsorption of the nitrogen oxide gas molecule on these materials are listed in the table. It is suggested that the solid surface could effectively capture the gas molecule when the adsorption energy is less than negative 0.5 electron volts, which will lead to longer recovery time or higher releasing temperature. Thus, the nitrogen oxide gas is less likely to escape from the surface of Ti2CCl2 and Mo2CO2 MXenes due to the relatively large adsorption energy for these materials. The relationship between the adsorption energy and the recovery time of these sensors is exponential. The recovery time of the sensor for materials with adsorption energy less than negative 0.7 electron volts is much higher when compared to other materials in the table. The adsorption energy of the nitrogen oxide and chlorine-terminated titanium carbide MXene system suggests that the nitrogen oxide gas will effectively adsorb on the chlorine-terminated titanium carbide MXene, but the gas molecule will not be captured on the surface. To further investigate the interactions between the nitrogen oxide gas molecule and the chlorine-terminated titanium carbide MXene, the density of states for the chlorine-terminated titanium carbide MXene and the adsorption of nitrogen oxide on chlorine-terminated titanium carbide MXene were obtained for studying the modulation of the electronic properties of chlorine-terminated titanium carbide MXene upon the adsorption of nitrogen oxide gas molecule. The Fermi energy level was set to 0 for density of states calculations. As can be seen from figure, the adsorption of the nitrogen oxide molecule increases the number of states close to the Fermi energy level, which can modulate the electronic properties of the chlorine-terminated titanium carbide MXene significantly. The adsorption of the nitrogen oxide molecule introduced new states around negative 8.5 electron volts as well, but these states do not have a significant role in the modulation of electronic properties because they are far from the Fermi energy level. The mechanism of gas sensing in MXenes primarily depends on the charge transfer between gas molecules and MXenes, which leads to conductivity modulation of MXenes. Charge density difference calculations were employed to study the charge transfer between the nitrogen oxide gas molecule and the chlorine-terminated titanium carbide MXene. The isosurfaces of charge density difference for the adsorption of nitrogen oxide molecule on chlorine-terminated titanium carbide MXene with a reference charge density of 0.007 electrons per angstrom cubed are illustrated in the figures. The accumulation and depletion of electrons are shown by the blue and red isosurfaces respectively. According to figures, the red isosurfaces around the oxygen atom show that the electron density around the oxygen atom is decreasing. Also, the large red area around the nitrogen atom reveals the charge transfer from the nitrogen oxide molecule to the MXene. The electron density around the titanium atoms increased upon the nitrogen oxide gas adsorption. In addition, the isosurfaces representation suggests that The contribution of carbon atoms to the charge transfer between the nitrogen oxide molecule and the MXene was much less than the contribution of titanium and chlorine atoms. In this work, DFT calculations were used to analyze the interactions between the nitrogen oxide gas molecule and chlorine-terminated titanium carbide MXene. The lattice constant of the chlorine-terminated titanium carbide MXene was obtained as 3.22 angstroms. The adsorption energy for the physisorption of the nitrogen oxide molecule on chlorine-terminated titanium carbide MXene was calculated as negative 0.5 electron volts. Density of states calculations showed the introduction of new states close to the Fermi energy level upon the adsorption of nitrogen oxide molecule on chlorine-terminated titanium carbide MXene, which can modulate the electron properties significantly. The charge density difference calculations showed the charge transfer from the nitrogen oxide molecule to the chlorine-terminated titanium carbide MXene. Selectivity is one of the most important parameters for the evaluating of the performance of a sensor. Previously, we had done selectivity study for MXene with a mixture of functional groups including fluorine, oxygen, and hydroxyl, as shown in the figure. Future work includes investigation of interactions between other gases and the chlorine-terminated titanium carbide MXene, which has exclusive chlorine surface terminations. Thank you very much for your attention. This work was supported in part by the Center for Advanced Smart Sensors and Structures, CAS, Western Michigan University. We would like to acknowledge graduate assistantship from Western Michigan University.